In this video, we're going to introduce chapter 23. And in part 1, we're going to talk about the induced electromotive force and magnetic flux. Then we'll talk about Faraday's law and Lenz law. So let's try to introduce what electromagnetic induction is all about. Now to do so, we're going to look at two devices. The first one is called an electric motor. So basically an electric motor converts electrical energy into mechanical energy, and this uses a uniform magnetic field. So the picture that you see on the right side here explains how an electric motor works. So we start with some power supply that is going to generate some current, and this current is going to go through a loop in the presence of some magnetic field. So again, this is the north and this is the south. So the magnetic field is going to generate forces on the left side and on the right side of the loop. Notice that the force on the left side is pointing into the paper, while the force on the right side is pointing out of the paper. So the combined effect of these two forces is going to generate a torque that is going to cause this loop to rotate in the clockwise direction. So again, basically what this is going on is that we're using energy, electrical energy, and converting that electrical energy into mechanical energy. Now, an electric generator converts mechanical energy into electrical energy, and this uses a changing magnetic field. So an example of an electric generator is the wind turbine. So in this example here, what you see is that so energy from the wind is going to push the blades of a turbine, spinning a shaft that is attached to the magnet. So the magnets are going to spin around a conducting coil, inducing an electric current in the coil. So again, what is important here is the spinning action of the magnets. So the spinning action of the magnets is what is going to be responsible for generating an electric current, and this is called the principle of electromagnetic induction. So we'll talk about this a little bit later on, but again, what the electric generator is doing is that it's just taking mechanical energy and converting that energy into electrical energy. So now let's talk a little bit about the symmetry between electricity and magnetism. So the picture that you see on the left side is a picture of a butterfly, and you can see that it has perfect symmetry. So if this is so notice that everything that you see here on the right side is just like a mirror image of what is on the left side. So just like there is a butterfly, which tells me about the symmetry in nature, there is also symmetry between electricity and magnetism. So what this means is that we can use electricity to produce magnetism, and also we can use magnetism to produce electricity. Now let's do a little bit of review. So this is something that we've already discussed in the previous video, but let's review a little bit about the magnetic fields from currents. So if you remember in the previous lecture, we said that we can produce magnetic fields from currents. And these three examples here show me how I can generate a magnetic field. So the first example on the left side here is this is a straight conductor that carries a current, and this will generate a magnetic field, and the magnitude of that magnetic field can be calculated using this equation. So again, I is the current in the wire, and R is just the distance from the wire. Now, if you take a conductor, a cable, and you make it into a loop and run some current through it, then this will also generate a magnetic field, and the magnetic field can be calculated using this equation here. So again, I is the current in the loop, and R is a radius, of the loop. So again, this will be the magnetic field at the center of the loop. And then we also said that we can have a solenoid here. So again, if you run some electric current through the solenoid, you generate a magnetic field that can be calculated using this equation here. So again, so what these three examples show me is that I can generate magnetic fields from currents. So now we can look at this question here. So can we also produce electric currents from a magnetic field? So Faraday's law of electromagnetic induction tells me that it is possible to produce electric currents from a magnetic field. And this is something that we're going to be talking about. So now we're going to get into section 23.1. So in this section, we'll talk about the induced electromotive force and the magnetic flux. So let's look at these 5 pictures right here. So in each of this picture, you can see that there is a bar magnet that has a north and a south, and then we have a coil that is connected to a galvanometer. Now the galvanometer can deflect to the right or to the left, depending on the direction of current, or the galvanometer will just stay stationary. It doesn't deflect if there is no current. So let's look at the first picture right here. So in the first picture, you have a bar magnet with the south at the bottom and the north at the top. So when you move this up through the coil, this will generate a current that is going in the clockwise direction, and this is going to cause the galvanometer to deflect to the right. Now, if you repeat the same experiment, but this time around, moving the bar magnet down, then you induce a current in the coil that is pointing in the clockwise direction, and this will cause the galvanometer to deflect to the left. Now, if we do a second experiment where we have the south at the top and the north at the bottom, and again, if we move this up, then we induce a current in the coil that is pointing in the counterclockwise direction, and this will cause the galvanometer to deflect to the left. And if you have a north at the bottom and a south at the top, and if you move it down, this will induce a current that is going in the clockwise direction, and again, this will cause the galvanometer to deflect to the right. Now, what if the bar magnet is not moving? So if the bar magnet is stationary, then there is no current induced in the coil, and in this case, there is no deflection in the galvanometer. So something that we want to take out of this is that is the moving action of the bar magnet that induces the current in the coil. So if you are not moving this bar magnet, you don't produce any current in the coil. Now, this is an example here. So this is a simulation of the induced electromotive force. So I can go in here. So I want to show what the magnetic field lines are. So notice that at this point, if the bar magnet is not moving, so this is my bar magnet here, and this is a coil, and this is the galvanometer. So notice that right now, the bar magnet is not moving, so there is no current, so there is no voltage in the galvanometer. But as I move the bar magnet to the right, you notice that there is going to be some changes current. Now, if that's at rest, nothing happens. So if you move it back out, so moving this in and out, you can see that you're inducing some current in the coil. So this illustrates the principle of electromagnetic induction. And the amount of current that you induce here depends on the speed. So if you move this at a faster speed, you generate, the magnitude of the current is going to increase with the speed at which you move the bar magnet into the coil. All right. So now let's talk a little bit about the principle of a generator. So we've said that a generator is going to take mechanical energy and convert that energy into electrical energy. So the picture that you see here, you have a loop in the presence of some uniform magnetic field. Now the point is that as you rotate this loop, right, the amount of magnetic field that is going to go through the surface of the loop is going to change. And it's that changing action of the amount of magnetic fields that go through the loop that is going to generate a current in this coil right here. So again, basically what we're doing is that we're using the mechanical energy here. So just by rotating this loop, we change the amount of magnetic field lines that go through the loop, and the changing action is what is responsible for generating a current. So a generator uses the principle of electromagnetic induction. All right. So now we're going to talk about magnetic flux. So the magnetic flux is a quantity that is given by this equation right here. So this is a symbol, is just the strength of the magnetic field times the area times the cosine of the angle between the magnetic field and the normal to the area. So this area is just the area of a coil or a loop. So the point is that the flux is going to be maximum when the theta is equal to 0. So when theta is equal to 0, it means that you have more magnetic fields that are going through this area. When theta is equal to 90 degrees, the magnetic field is actually perpendicular to the normal to the area, and in that case, the flux is just going to be equal to 0. Now, the principle of electromagnetic induction simply says that any change in the magnetic flux is going to induce an electromotive force. So the flux is given by this equation here, and I just want to mention that the units of the magnetic flux is Teslas meter square. All right, so now we'll go into section 23.2, and in this section we're going to talk about the Faraday's law and the Lenz law. So the Faraday's law of induction simply says that a change in magnetic flux is going to induce an electromotive force in a coil, and is given by this equation right here. So if you have a coil that has n turns, then the change in the electromotive force is given by this equation. It's just the number of turns times the change in the magnetic flux with respect to time. Now, so Faraday's law kind of tell me how I can calculate the magnitude of the electromotive force. Now, Lenz's law tells me how I can calculate the direction of the current. So Lenz's law simply tells me that the induced electromotive force creates a current and a magnetic field that oppose the change in the flux. So I'll just take one example here, but suppose that you have, this is the south and this is the north, and you have a magnetic field. So again, if this is the south and this is the north, we know that the magnetic field lines are always going to point from the north to the south. So B magnet is the magnetic field produced by this bar magnet. So when you bring this bar magnet towards this coil, notice that so it's going to generate a current in the coil in such a way that the current itself in the coil is going to produce a magnetic field that is going to point in the opposite direction to the magnetic field produced by the bar magnet. So for this example right here, by moving this bar magnet from left to right, the current is going to flow in such a way that the magnetic field of the coil should be pointing to the left. So in this example right here, you can notice that the current is flowing in the counterclockwise direction. All right. So at this point, I just want to go over one example here. So this is example number 23.1. So we're going to calculate the electromotive force. So what this example tells us is that so want to calculate the induced electromagnetic force when a magnet is placed in a coil, and then it tells us that the coil has a radius of 6.0 centimeters, and the average value of the magnetic field increases from 0.05 to 0.25 Teslas in 0.10 second. So since we know what the change of the magnetic flux is, so we're saying, so in this example, the magnetic field is not constant, but it's changing. So it goes from 0.05 to 0.25 Teslas in 0.10 second. So now I want to use this equation here to calculate the induced electromotive force. So n equals to 1 because there is just one coil. And then we know what the change in time is 0.1 second. So I can use that information. Like first I want to calculate the area, and then I can multiply the area by the change in the magnetic field. So the change in the magnetic field is 0.2 as you go from 0.05 to 0.25, so the change is 0.2. So if you multiply that by the area, you get a change in the flux, which is given by that equation. And then if you plug that into this equation right here, you can calculate the change in the EMF and this will just be 22.6 millivolt.